Hi everyone, this is Ranjit from Cybersecurity Section. 2295 and 626 is my roll number. Today's topic is integral and Hermitian matrix. Introduction. In mathematics, a Hermitian matrix or self-adjoint matrix is a complex square complex square matrix that is equal to one transpose, that is the element in the ith row and jth column is equal to complex conjugate of the element but jth and ith column for all incidents I and j. The Hermitian is equal to Aij equals to Aji bar for a matrix from A Hermitian is equal to A equals to A transpose bar. Hermitian matrix can be understood as the complex extension of real symmetric matrices. If the conjugate transpose of a matrix A is denoted by the Hermitian properly can be written as A Hermitian is equals to A is equals to A power H. Hermitian matrices are named after Charles Hermite, who demonstrated in 1855 that matrices of this group share a property with real symmetric matrices of always having real eigenvalues. Other equivalent notations in common use are A power H equals to A power F is equals to A power star. Although note that in quantum mechanics, A power star typically means the complex conjugate only and not the conjugate transpose. Alternate characterization. Hermitian matrices can be characterized in a number of equivalent ways, some of which are listed below. Equality with the adjoint. A square matrix A is Hermitian if and only if it is equal to its adjoint. That is, it satisfies W comma AV is equals to AW comma V. For any pair of vectors VW where dot comma dot denotes the interproduct operation. This is also the way that the more general concept of self-adjoint operator is defined. Reality of quadratic forms. And n greater or less than n matrix n into n matrix A is Hermitian if and only if V comma maybe it belongs to R. V belongs to C power n. Spectral properties. A square matrix A is Hermitian if and only if it is unitarily diagonalized with real eigenvalues. Applications. Hermitian matrices are fundamental to quantum mechanics because they describe operators with necessarily real eigenvalues. An eigenvalue of an operator on some quantum rate A bar is one of the possible measurement outcomes of the operator, which necessitates the need for operators with real eigenvalues. Examples and solutions. In this section, the conjugate transpose of matrix A is denoted as A power H. The transpose of matrix A is denoted as A power T. And conjugate of matrix A is denoted as A bar. Now the matrix 0. Now the 3 by 3 matrix 0. A minus IB, C minus ID, A plus IB 1, M minus IN, C plus ID, M plus IN 2. The diagonal elements must be real as they must be their own complex conjugate. Well-known families of Hermitian matrices include the Pauling matrices, the Gell-Mann matrices, and their generalizations. In theoretically, physics such as Hermitian matrices are often multiplied by imaginary coefficients, 1 or 2, which results in skew Hermitian matrices. Here we offer another way for Hermitian matrix using an abstract example. A square matrix A equals the multiplication of a matrix and its conjugate transpose, that is A is equals to B power H. Then A is a Hermitian positive semi-defined definite matrix. Furthermore, if B is a row full rank, then A is positive definite. Main diagonal values are real. The entire on the main diagonal, top left to bottom right of an Hermitian matrix are real. By definition of the Hermitian matrix, Hij is equals to Hji bar. For I is equals to j, the above follows. Only the main diagonal entire are necessarily real. Hermitian matrices can be have arbitrary complex values entire in their off diagonal elements as long as diagonally opposite entire are complex conjugates. Symmetric. A matrix that has only real entries is symmetric if and only if Hermitian matrix A real and symmetric matrix is simple. A special case of a Hermitian matrix. Proof. Hij J is equals to Hij J bar by definition. Thus, Hij J is equals to Hji. Matrix symmetry. If and only if Hij J is equals to Hij bar. Hij is real. So, if a real antisymmetric matrix is multiplied by a multiple of imaginary unit I, then it becomes Hermitian. Normal. Every Hermitian matrix is a normal matrix. That is to say A power H is equals to A power H. Proof. A is equals to A power H. So A power H is equals to A into A, which is equals to A power H into A. Diagonalizable. The finite dimensional spectral theorem says that an Hermitian matrix can be diagonalized by unitary matrix unitary matrix and that the resulting diagonalizing matrix has only real entries. This implies that all eigenvalues of a matrix A with dimension n are real and that A has n linearly independent eigenvectors. Moreover, a Hermitian matrix has orthogonal eigenvectors for distinct eigenvalues. Even if there are degenerate eigenvalues, it is always possible to find an orthogonal basis of Cn consisting of n eigenvectors of M. Sum of Hermitian matrices. Sum of any two Hermitian matrices is Hermitian. A plus B of Ij equals to Aij plus Bij, which is equals to Aij bar, Abi bar plus Bji bar is equals to A plus Bji whole bar as claimed. Inverse is Hermitian. The inverse of an invertible Hermitian matrix is Hermitian as well. Proof. If A inverse into A is equals to I, then I is equals to I power H. Is equals to A inverse into A whole power H. A power H is equals to A power H of A inverse of H is equals to A into A inverse of H. So A inverse is equals to A inverse of H as claimed. Associative product of Hermitian matrices. The product of two Hermitian matrices A and B is Hermitian if and only if AB is equals to BA. Proof. Note that AB whole power H is equals to AB transpose bar is equals to B transpose A transpose bar is equals to B transpose bar into A transpose bar is equals to B power H into A power H, which is equals to BA. Thus, AB whole power H is equals to AB if and only if AB is equals to BA. Thus an An is Hermitian if A is Hermitian and N is an integer. Thus, AN is Hermitian if A is Hermitian and N is an integer. ABA Hermitian. If A and B are Hermitian, then ABA is also Hermitian. Proof. ABA whole power H is equals to A into B power N whole power H. BA B into A whole power H into A power H. A power H into B power H into A power H, which is equals to ABA. VHAV is real for complex V. For an arbitrary complex valued vector V, the product V power H AV is real because of V power H AV is equals to V power H AV whole power H. This is especially important in quantum physics where Hermitian matrices are operators that measure properties of a system. Example, total spin which have to be real. Complex Hermitian forms vector space overall. The Hermitian complex n by n matrices do not form a vector space over the numbers since the identified matrix in is Hermitian, but In is not. However, the complex Hermitian matrices do form a vector space over the real numbers R. In the 2 and 2-dimensional vector space of complex n into n matrix over R, the complex Hermitian matrix for a subspace of dimension n2 if EJK denotes the n by n matrix with a 1 in j comma k position and zeros elsewhere. A batch is orthogonal with respect to the four-binary inner product can be described as follows. Eij for 1 is less than or equal to j is less than or equal to n matrices together with the set of matrices of the form 1 by root 2 of Ejk plus Ekj for 1 less than or equal to j less than k less than or equal to n, which is n square minus n by 2 matrices. And the matrices I by under root 2 Ejk minus Ekj for 1 less than or equal to j less than k is less than or equal to m for n square minus n by 2 matrices, where I denotes the imaginary unit I is equals to under root minus 1. An example is that 4 poly matrices form a complete basis for the vector space of all complex 2 by 2 Hermitian matrices over R. Eigen, eigen decomposition. If n, n orthonormal eigenvectors U1 and so on U1 of a Hermitian matrix are chosen and written as the columns of matrix U, then one eigen decomposition of A is equals to UA where U into UH is equals to I is equals to UH in U, and therefore A is equals to sum of J to I lambda J UJH, where lambda J are the eigenvalues on the diagonal of diagonal matrix A. Real determinant. The determinant of Hermitian matrix is real. Proof. Delta is equals to det delta of A is equals to delta of A transpose. Delta of A power H is equals to delta of A whole bar. Therefore, if A is equals to A power H, delta of A is equals to delta of A bar. Alternatively, the determinant is the product of the matrix eigenvalues, and as mentioned before, the eigenvalues of Hermitian matrix are real. Decomposition. Decomposition into Hermitian and skew Hermitian matrices. Additional facts related to Hermitian matrix include the sum of a square matrix and its conjugate times A plus A power H is Hermitian. The difference of a square matrix and its conjugate times A to A power H is skew Hermitian, also called anti-Hermitian. This implies that the commutator of two Hermitian matrices Q Hermitian and arbitrary square matrix C can be written as the sum of the Hermitian matrix A and the skew Hermitian matrix B. This is known as the triplex decomposition of C. C is equals to A plus B with A is equals to 1 by 2 C of C plus C power H and B is equals to 1 by 2 of C minus C power H. Rayleigh equation. In mathematics, for a given complex Hermitian matrix M and non-zero vector X, the Rayleigh equation R of m comma x defined as R of m comma x, R of m comma x is equals to x power h mx by x power h for real matrices and vectors. The condition being Hermitian reduces that of being symmetric and the conjugate transpose x power h to the usual transpose x power t. Note that R of m comma cx is equals to R of m comma x. For any non-zero real scalar, see also recall that a Hermitian or real symmetric matrix has real eigenvalues. It can be shown. It can be shown. Citation needed that for a given matrix, the Rayleigh quotient reaches its minimum value, lambda minimum, where x is V minimum. The corresponding eigenvector similarly R of m comma x is not equal to lambda max and R of m comma V max is equals to lambda max. The Rayleigh equation is used in the minimum to maximum theorem to get exact value of all eigenvalues. It is also used in eigenvalue algorithms to obtain an eigenvalue approximation for an eigenvector approximation. Specifically, this is the basis for Rayleigh quotient interaction. The range of the Rayleigh quotient for matrix that is not necessarily Hermitian is called a numerical range or spectrum in functional analysis. When the matrix is Hermitian, the numerical range is equal to spectral norm. Still, in functional analysis, lambda max is known as the spectral radius. In the context of C power star algebras or algebraic quantum mechanics, the functions that 2m associates the Rayleigh quotient R of m comma x for fixed x and varying through algebra would be referred to as vector state of the algebra. This is about the presentation. Thank you.